It begins not with a weather forecast, but with a ghost. A ghost of water, of wind, of a geometry that has not yet repeated itself in living memory, but which has left its signature written in the bones of the continent. In the year 1821, a hurricane made landfall in what would one day become New York City. But this was not the New York we know. There were no subways to flood, no high-rise glass facades to shatter, no underground electrical vaults to ignite. The island of Manhattan in 1821 was still largely pastoral, its shoreline low and open to the sea. And yet, the storm pushed a surge of water into the narrow throat of New York Harbor that rose, by the accounts of those who survived it, 13 feet in less than an hour. Water rushed across the southern tip of the island, as far north as Canal Street. That is a fact preserved in yellowed newspapers and maritime logs. Hold that fact for a moment. Canal Street. Today, Canal Street is a congested artery of Chinatown, a thoroughfare lined with shops and subway entrances, home to tens of thousands of people who sleep in apartments built atop the very ground that was 2 centuries ago underwater. The storm of 1821 was not a warning from a computer model. It was not a projection of a warming climate. It was a thing that happened. It is a thing that has already occurred on this exact geography, and no living person remembers it. Memory, unlike data, decays with each generation, but physics does not forget. The same astronomical alignments that produced that storm, the gravitational pull of the moon and sun at their most conspiratorial, the specific steering currents of the Atlantic hurricane track, the bathymetry of the Hudson Shelf Valley, have not been erased. They have simply been waiting for the right conditions to reassemble. What we are about to examine is not a hypothetical future. It is a historical event that has already proven itself possible, and which modern infrastructure has rendered far more dangerous than the original ever was. The storm is old. The vulnerability is new. To understand why this particular combination of forces matters, we have to hold 2 apparently contradictory facts in our minds at the same time. The first fact is that New York City has, in the last decade, experienced 2 major water events that each exposed a different half of a much larger systemic failure. The second fact is that neither of those events was the worst-case scenario. They were, in retrospect, dress rehearsals. The first event was Hurricane Sandy in 2012. Sandy was a post-tropical cyclone of unusual size and trajectory. It did not hit New York City with the highest winds ever recorded. It did not bring the most rain. What Sandy did was demonstrate something more insidious: the vulnerability of the city's circulatory system to a single, precisely timed surge. The surge from Sandy reached a height of about 14 feet above mean low water at the Battery. That number is precise. It is measured, and it is worth being clear about what 14 feet means in 3 dimensions. 14 feet of water is enough to submerge the entire ground floor of most buildings south of 34th Street. It is enough to fill every subway tunnel that enters Manhattan from Brooklyn or New Jersey. It is enough to pour into the ventilation shafts of the PATH train system and the underground roadways of the Brooklyn Battery Tunnel. And that is exactly what happened. Sandy drowned the subway. It turned the underground rail network into a series of connected saltwater basins. The water did not merely flood stations, it flowed through the tunnels themselves, traveling for miles beneath the East River, emerging in places where no direct surface connection existed. The Rector Street Station, the South Ferry Station, the entire complex of infrastructure that moves millions of people daily, stopped. The pumps that were designed to remove water from the subway system were themselves submerged. because the pumps live in the lowest points of the tunnels, and the lowest points of the tunnels are exactly where the water goes first. That is a design flaw that is not a flaw. It is an artifact of an assumption. The assumption was that the water would never reach the pumps. But the water did reach the pumps, and the water went where water goes. This is not a moral statement about the storm. It is a description of physics. Water flows downhill. The subway is downhill. Therefore, the subway is a riverbed when the city is a basin. But here is where the story becomes more interesting and more troubling. Sandy exposed the external threat. The ocean, pushed by wind and tide, invaded the city from outside. That was the macro threat. And in the aftermath of Sandy, billions of dollars were spent to begin building defenses against that kind of invasion. Seawalls were studied. Floodgates were designed for the mouth of New York Harbor. The city began to think of itself as a fortress against the sea. That was the correct engineering response to the data. But there was another event, almost a decade later, that revealed a different vulnerability entirely. In September of 2021, the remnants of Hurricane Ida moved across the northeastern United States. By the time Ida reached New York, it was no longer a hurricane in the meteorological sense. It was a tropical depression carrying an immense load of atmospheric moisture. The rain began in the late afternoon, and it did not stop. Over the course of a few hours, parts of New York City received more than 3 inches of rain per hour. That number does not sound dramatic until you understand what it means for a city built on a grid. The drainage system of New York was designed for a storm of a certain statistical return interval, a 1 in 10-year storm, a 1 in 20-year storm. Ida delivered rainfall rates that exceeded the design capacity of the drainage system by such a margin that the water had nowhere to go. The streets became canals because the sewers were already full, and the sewers were full because they drained to the same harbor that was, on that night, also being pushed by a tide that had nowhere to receive the outflow. When the drainage system backs up, the water does not vanish. It pools, and in a city of paved surfaces, the only places for water to pool are the lowest points in the terrain, which are the same points that were in the 19th century streams and wetlands, the same points where, today, basement apartments are rented to people who have no other housing options. Ida killed 13 people in New York City. Almost all of them drowned in basement apartments. They were not killed by the ocean. They were killed by rain. Rain that fell on a city that had spent its defense budget on walls against the sea, not on pumps for the streets. This is the second fact that must be held next to the first. Sandy was an invasion from outside. Ida was a trap from within, and the city survived both. But the question that haunts the engineers, the hydrologists, and anyone who has looked at the historical record of 1821 is this: what happens when the invasion from outside and the trap from within arrive on the same day? Let us be precise about what that would require. For a storm to flood New York City beyond saving, it does not need to be the strongest hurricane ever measured. It does not need to be a Category 5. What it needs is a specific temporal alignment of 3 independent factors. The first factor is the tide. The gravitational pull of the moon and sun create a twice-daily rhythm of rising and falling water. But every 2 weeks, when the moon and sun align with Earth, the tidal range is larger. These are spring tides. They are predictable. They are on the calendar. The second factor is the storm surge itself, a tropical cyclone moving across the Atlantic and into the New York Bight pushes a dome of water ahead of it. The height of that dome depends on the storm's intensity, its forward speed, and the shape of the ocean floor. The Hudson Shelf Valley, a submerged canyon that extends from the continental shelf almost to the entrance of the harbor, acts as a funnel. It concentrates surge energy into a narrowing channel. That is bathymetry, that is fixed, that cannot be changed. The third factor is the rain. A slow-moving storm that stalls over the metropolitan area can deposit rainfall at rates that overwhelm the combined sewer system. But here is the paradox. The same atmospheric dynamics that produce a large storm surge, a strong, broad circulation, tend to move the storm quickly. A fast-moving storm produces less rain over a given location. A slow-moving storm produces more rain but less surge because the wind field has less time to pile water against the coast. The worst-case scenario requires a storm that is both strong enough to produce a large surge and slow enough to produce extreme rainfall. That combination is rare. It is the hydrological equivalent of a perfect hand in cards. But rarity is not impossibility. And the historical record of 1821 tells us that this combination has already occurred, at least once before the era of modern measurements. The surge was 13 feet at the Battery. The rain gauges of 1821 were primitive, but the accounts describe rain that fell for hours without slackening. The storm moved slowly enough to flood the island to Canal Street. That is the baseline. That is the precedent. Now we must add the layer that makes the historical event irrelevant as a direct comparison. In 1821, the population of Manhattan was around 150,000 people. Most of them lived above Canal Street. The flooded area was largely undeveloped or consisted of low-rise buildings with open ground floors. The water rose and then it receded. There were no subway tunnels to trap the water. There were no underground electrical substations to explode. There were no high-rise apartment buildings whose ground floor lobbies contained the fire pumps and electrical switchgear for 40 floors of residences. The water in 1821 went where water goes, and then it left. The water in a future storm will go where water goes, but it will encounter a built environment that functions like a sealed container. The subway system alone contains hundreds of miles of tunnels, many of which are below the water table even on a dry day. Those tunnels are kept dry by a network of pumps that require electricity. The electricity comes from substations that are, in many cases, located below the flood level. In Sandy, the pumps failed because the substations failed. The water reached the pumps before the pumps could remove the water. That is a closed loop of failure. It is not a design flaw that can be fixed by adding more pumps. It is a topological problem. The pumps live at the bottom. Water flows to the bottom. Therefore, the pumps will always be the first thing to drown. The only solution is to prevent the water from reaching the bottom in the first place. But preventing water from reaching the bottom means building barriers at the entrances to every tunnel, every vent shaft, every stairwell. That is thousands of points of vulnerability. And each barrier must be deployed before the water arrives. And the water will arrive faster than any human-operated system can respond, because the water is not waiting for permission. The water is simply following gravity. Let us expand the scale of this thought. The New York metropolitan area is not a collection of separate municipalities. It is a single organism with a circulatory system of roads, rails, power lines, water pipes, and data cables. Drown one organ, and the others begin to fail through cascading dependency. In Sandy, when the subway drowned, the streets above became impassable because the traffic lights lost power. The traffic lights lost power because the electrical substations in the flood zone tripped offline. The electrical substations tripped because the water conducted faults to ground. The faults occurred because the water was salt water, which is conductive. Fresh water from rain alone would have caused less immediate damage to electrical systems. But the surge from the ocean brings salt water, and salt water is an electrolyte. It completes circuits that were never meant to be completed. It turns the city into a short circuit. The cascades continue. When the traffic lights fail, emergency vehicles cannot reach flooded areas. When emergency vehicles cannot reach flooded areas, people trapped in basements cannot be rescued. When people cannot be rescued, they drown. That is not a hypothetical chain. That is the chain that occurred in Sandy and Ida separately. In a combined event, the chain is compressed. The surge drowns the electrical infrastructure at the same time that the rain drowns the drainage system, at the same time that the tide prevents the drainage system from outflowing. The three factors do not add linearly. They multiply. Because a drainage system that is blocked by a high tide is a drainage system that cannot remove the rain. And a power grid that is offline is a power grid that cannot run the pumps. And pumps that cannot run are pumps that cannot remove the water from the tunnels. And tunnels that fill with water become barriers to evacuation, barriers to rescue, barriers to any movement across the city. The city becomes an archipelago of dry islands separated by impassable channels of water that are not rivers but former streets. And on those islands, people will be trapped in high-rise buildings that have lost power, lost water pressure, lost the ability to flush toilets or pump drinking water to upper floors. Because the water pressure in a tall building comes from pumps in the basement, and the basement is already full. This is the point where the narrative must pause and ask a deeper question. Why has this not happened yet? If the conditions are possible, if the precedent exists, if the infrastructure is so vulnerable, why has the city not already been destroyed? The answer is statistical. The return period of a storm that aligns high tide, maximum surge, and extreme rainfall in the same window of hours is long. Perhaps 100 years, perhaps 500. The problem is that the return period is not fixed. It is changing because the climate is changing. Warmer air holds more water vapor. More water vapor means more potential rainfall. Warmer ocean temperatures mean more energy for tropical cyclones. The distribution of storm tracks is shifting. The historical return periods are artifacts of a climate that no longer exists. What was a 1 in 500-year event in 1821 may be a 1 in 50-year event by the middle of this century. That is not a forecast. That is a calculation based on the Clausius-Clapeyron relationship, which is a law of physics. For every degree Celsius of warming, the atmosphere can hold about 7% more water vapor. The planet has already warmed more than 1 degree. The rainfall potential of any given storm has already increased. The surge potential has increased because sea level has risen. The baseline from which the surge is measured is higher. A 13-foot surge in 1821 is a 13-foot surge today, but today the starting point is almost a foot higher due to sea level rise alone. So the water reaches farther inland. It reaches streets that were dry in 1821. It reaches subway entrances that did not exist. It reaches basement apartments that house people who cannot afford to live anywhere else. The social vulnerability is the final multiplier. The people who drown in these events are not random. They are the people who live in the lowest lying apartments. The people who cannot evacuate because they have no car, no savings for a hotel, no family outside the city. The people whose landlords did not install backflow valves on the drains. The people who are, in the most brutal sense, occupying the terrain that the water has historically claimed as its own. The water does not know this. The water does not choose. But the water goes where water goes, and in New York City, where water goes is increasingly where people sleep. The engineering response to this threat has been ambitious and incomplete. After Sandy, the city began planning the Big U, a system of flood barriers, berms, and deployable walls that would wrap the most vulnerable parts of Manhattan from West 57th Street down to the Battery and up to East 42nd Street. The concept is elegant, the implementation is slow, and the fundamental limitation of any perimeter defense is that it defends a perimeter. It assumes that the threat comes from outside, but Ida demonstrated that the threat also comes from above. Rain does not respect flood walls. Rain falls inside the perimeter. And when the perimeter is sealed to keep the ocean out, the rain has nowhere to go. The drainage system becomes a bathtub drain with the stopper half closed. The solution to that paradox is not simple. It requires rethinking the entire relationship between the city and water. It requires elevating subway entrances, installing stormwater pumps on every block, retrofitting basement apartments with flood vents, moving electrical infrastructure to higher floors, and accepting that some neighborhoods may need to be abandoned to the tide. That is not defeatism. That is realism. But realism is expensive, and the cost of doing nothing is not zero. It is simply deferred. The water will collect its debt eventually. The only question is whether the city pays in dollars now or in lives later. Let us return to the ghost of 1821. That storm did not know it was a warning. It was just a storm. It did what storms do. But the people who witnessed it wrote down what they saw. They described water rushing up from the Battery, covering wharves and warehouses, floating ships into the streets. They described a wall of water that moved so quickly that there was no time to run. They described the smell of salt and mud and the strange silence after the surge receded, when the only sound was the dripping of water from the rafters of buildings that had never expected to be underwater. Those descriptions are not literature. They are data. They are the only data we have from the last time the perfect alignment occurred. And if we read them carefully, we can extract a prediction. The next perfect alignment will not announce itself with a wall of water from the harbor alone. It will announce itself with rain that does not stop, with a tide that will not go out, with a surge that arrives at the worst possible moment, and with a city that watches its own infrastructure turn against it. The subways will fill. The power will fail. The pumps will drown. The streets will become rivers. The rivers will become lakes. And the lakes will cover the place where millions of people now sleep. This is not a forecast. It is an extrapolation from a single historical data point. But that is how all science works. We observe what happened. We identify the conditions. We project forward. And we ask ourselves whether we are willing to act on the information before the information becomes experience. The deeper implication, the one that moves this from a matter of civil engineering to a matter of existential uncertainty, is that our infrastructure is built on an assumption of stationarity, the assumption that the past is a reliable guide to the future, that the 100-year flood will occur on average once every 100 years, that the climate in which our grandparents lived is the climate in which our grandchildren will live. That assumption is now false. It is not slightly damaged. It is not in need of revision. It is false in a fundamental physical sense. The atmosphere is not the same atmosphere. The ocean is not the same ocean. The statistical distributions that engineers use to design storm drains and seawalls are extrapolations from a world that no longer exists. We are building defenses against the past, while the future arrives from a direction we did not anticipate. That is not a failure of engineering. It is a failure of the imagination. And the imagination is the only tool that can save us, because the imagination is what allows us to see the storm of 1821 not as ancient history, but as a message that says, this has happened before, it can happen again. And next time the consequences will be measured not in feet of water, but in the number of people who did not know that the water was coming, because they had never been told about the storm that nobody remembers. The final layer of this exploration is the most unsettling. It is not about the storm. It is about the nature of risk itself. Humans are not good at evaluating low-probability, high-consequence events. Our brains evolved to respond to immediate threats, the rustle in the grass, the shadow on the horizon. A storm that has a 1% chance of occurring in any given year does not trigger that response. 1% feels small, but 1% per year over a 30-year mortgage means a 26% chance of experiencing the event during the time you own your home. That is not small. That is a roll of a four-sided die. And yet we behave as if the event will not happen. We build on floodplains. We rent basement apartments. We vote against tax increases for flood protection. We are not irrational. We are human. And our humanity is the variable that cannot be engineered away. The water will follow the physics. The city will follow the psychology. And the gap between those two trajectories is where the disaster lives. We began with a ghost. A storm from 1821 that flooded Manhattan to Canal Street. We have traced the two halves of the threat. The surge from the ocean that drowns the circulatory system, and the rain from the sky that traps the city in its own drained geometry. We have seen the cascades, the dependencies, the multiplying failures that turn a meteorological event into a civilizational test, and we have arrived at the only conclusion that the data supports. The perfect storm is not a question of if, it is a question of when. The only remaining uncertainty is whether the city will have prepared for the storm that happened 2 centuries ago or the storm that will happen tomorrow. The water is not waiting for the answer. The water is patient. The water has all the time it needs, and somewhere in the Atlantic, in the warm waters of the Gulf Stream, the next alignment is already beginning to form. The moon and the sun are pulling on the ocean as they always have. The tide tables for the year 2050 are already calculated. The storm itself has not yet been born, but the conditions that will give it life are accumulating, degree by degree, centimeter by centimeter, in the quiet chemistry of a warming planet. When it arrives, it will not knock. It will simply rise. And the only question worth asking now, the question that sits at the intersection of hydrology and human nature, is this. Will we recognize the storm of 1821 when we see it again? Or will we mistake it for something new, something unprecedented, something we could not have prevented? Because the truth is more uncomfortable than ignorance. The truth is that we know exactly what is coming. We have known since the water receded from Canal Street 200 years ago. The knowledge has not saved us. And that is the deepest mystery of all. Not whether the storm will come, but why we have chosen, collectively, to act as if it will not. The knowledge has not saved us. And that is the deepest mystery of all. Not whether the storm will come, but why we have chosen, collectively, to act as if it will not. But let us stop there for a moment, because that question, why we do not act, is itself a kind of trap. It assumes that inaction is a choice, a failure of will, a moral weakness. What if the truth is more unsettling? What if our inaction is not a choice, but a consequence of the way our brains process time? We are exquisitely adapted to respond to threats that arrive in milliseconds. A car swerving into our lane, a branch falling from a tree. But a threat that accumulates over decades, that builds itself into the infrastructure of a city like rust building in the rebar of a bridge. That threat does not trigger the alarm circuits in the amygdala. It triggers the narrative circuits in the prefrontal cortex. And narrative circuits do not produce action. They produce stories. We tell ourselves the story of the storm that is coming. We feel a small pulse of concern. And then we move on to the next story. The storm remains in the realm of imagination, not experience. And the gap between imagination and experience is where all preventable disasters live. Consider what it would actually feel like to be inside the perfect storm, not the aftermath, not the news report. The moment, the hour. The long, dark night when the water is rising and the power is gone, and the only sound is the rush of water through streets that were, 12 hours ago, filled with taxis and pedestrians and the ordinary noise of a living city. Let us be explicit about the sequence, because the sequence is the only thing that will save you if you are ever caught in it. And the sequence is the only thing that might persuade you to care before it happens. The storm does not begin with drama. It begins with a weather forecast that you half watch while making dinner. A tropical storm, they say, maybe a Category 1 hurricane by the time it reaches the coast. Nothing like Sandy, nothing to worry about. You have heard this before. You have weathered nor'easters and thunderstorms and the occasional tropical remnant that drops a lot of rain and then moves on. You check the flood zone map on your phone. You are in Zone 2, which means you might need to evacuate if it gets really bad, but it never gets really bad. You go to sleep. The rain begins around 2 in the morning, not heavy at first. A steady, persistent rain that sounds like static on a radio. The wind picks up around 4. You wake to the sound of something metal scraping against pavement outside. A trash can, maybe. A sign. You roll over and go back to sleep. At dawn, you look out the window. The street is a river, not a puddle, not standing water. A river moving from north to south, carrying debris, carrying the contents of someone's basement that has already flooded. You check the news. The subways are closed. The tunnels are closed. The bridges are closed because the wind is too high. You are on an island, and all the exits are sealed. This is not an evacuation. This is a siege. Now the tide begins to rise. This is the detail that most people miss. The surge from the storm does not arrive as a single wave. It arrives as a plateau. The wind pushes water into the harbor, and the water level rises and stays risen because the wind does not stop. The tide cycle continues underneath the surge. The moon is still pulling, so the water level oscillates on top of the surge, but the low tide of the surge is higher than the normal high tide. The high tide of the surge is a catastrophe. That is the window. That is the alignment. And on the day of the perfect storm, the high tide arrives at the same time as the peak of the surge. The water does not rise slowly. It rises at the rate the wind pushes it. And the wind is pushing at 60, 70, 80 miles per hour across 100 miles of ocean. The water has momentum. It has weight. A cubic meter of seawater weighs more than a ton. Now imagine a wall of that water. moving at the speed of a car on a city street, slamming into the Battery. The seawall at Battery Park, if it has been built by the time this storm arrives, will do its job. It will deflect the initial impact. But water does not give up. It goes around. It goes through the gaps. It finds the storm drains that were never designed for reverse flow and pours out of them into the streets behind the wall. It finds the subway entrances that were elevated by a foot or two, but not by 6. It fills the gaps in the flood barrier system, because every barrier system has gaps. They are called stations. They are called intersections. They are called the places where you cannot build a wall, because people need to move through. The water finds those gaps, because the water is not malicious. It is simply opportunistic. And opportunism, in hydrology, is indistinguishable from inevitability. Let us go underground, because this is where the true horror of the perfect storm resides. Not on the streets, where at least you can see the water coming. Underground, where the water arrives silently, without warning, filling the tunnels like an hourglass filling from the bottom. The subway system of New York has 472 stations. Most of them are below the water table. They are kept dry by pumps that run continuously, every day, every hour, moving millions of gallons of groundwater that would otherwise fill the tunnels. Those pumps are the only thing standing between a dry tunnel and an underwater tunnel. They are electric. They are located at the lowest points in the system, and they are designed to handle the normal inflow of groundwater, plus a moderate amount of stormwater from street drains that connect to the system. They are not designed to handle the entire volume of New York Harbor flowing through a single ventilation shaft. When the surge comes, the water pressure at the tunnel entrances is immense. The tunnel doors, the ones that are supposed to seal the system, are rated for a certain pressure differential. The surge exceeds that pressure within the first hour. The seals fail, not dramatically, not with an explosion, with a leak, then a trickle, then a flow, then a torrent. The water enters the tunnels and begins to move inward, seeking the lowest point. The lowest point in the entire subway system is the tunnel between Manhattan and Queens under the East River. It is more than 100 feet below the surface. That tunnel becomes a siphon. Water pours into it from both ends and fills it like a straw dropped into a glass. Once the tunnel is full, the water begins to rise up the stations on either side. The station at 14th Street. The station at 23rd Street. The water rises up the stairwells, up the elevator shafts, up the emergency exits. It emerges on the streets not as a flood from above, but as a flood from below. The city is not being drowned by the ocean. It is being drowned by its own circulatory system, which has been converted into a network of rivers flowing in reverse. Now add the rain. Because the surge is only half of the equation. While the ocean is invading from below, the sky is attacking from above. The rain has been falling for 12 hours. The sewers are full. The streets are already flooded to the height of the curb, then to the height of the first step of every building, then to the height of the first floor. The drainage system cannot keep up, because the drainage system outflows to the same harbor that is currently being pushed inland by the wind. The water has nowhere to go. So it pools. It fills the basements. It fills the sub-basements. It fills the underground parking garages. It fills the electrical vaults that contain the transformers for entire city blocks. Those transformers are filled with oil. The oil is dielectric, meaning it does not conduct electricity. But it is also lighter than water. When water enters a transformer vault, the oil floats to the top. The water fills the bottom. The electrical connections sit somewhere in between, When the water rises high enough to reach the connections, the system short-circuits. The breakers trip, the lights go out, not block by block, but in surges. A transformer blows, the grid reroutes. Another transformer blows, the grid reroutes again. Eventually, there are no more reroutes. The entire section of the city goes dark. And in the darkness, the pumps stop. The pumps that were keeping the subways dry stop. The pumps that were keeping the basement of your apartment building dry stop. The pumps that were keeping the hospital's emergency generators cool stop. Everything stops. This is the moment when the perfect storm becomes the unsurvivable storm. Not because the water is too deep, though it is. Not because the wind is too strong, though it is. But because the systems that enable evacuation, rescue, and survival have all failed simultaneously. You cannot call for help because the cell towers have lost power. You cannot drive to safety because the roads are under 6 feet of water. You cannot walk to safety because the currents in the streets are strong enough to sweep you off your feet. You cannot wait for rescue because the rescue boats cannot navigate the submerged streets filled with submerged cars and submerged debris. You are trapped in a building that is slowly filling from the bottom. You climb the stairs. You climb to the second floor. The water follows. You climb to the third floor. The water follows. You climb to the roof. The water stops rising eventually because the surge has a maximum height. But the rain continues, and the wind continues, and the cold continues because it is autumn. Because the perfect storm arrives in October or November, when the water temperature is low enough to cause hypothermia in minutes. You huddle on the roof with your neighbors, with strangers, with the people from the basement apartment who managed to climb the stairs before the stairwell became a waterfall. You wait for the tide to turn. You wait for the wind to shift. You wait for the water to recede. And eventually, it does. The storm passes, the surge retreats, the rain stops, the water level drops, but the city does not come back to life. Because the infrastructure that makes the city livable is dead. The subways are full of salt water, the electrical system is destroyed, the water supply is contaminated, the sewage system is backed up, the hospitals are running on generators that will fail when the fuel runs out. The airports are lakes, the bridges are damaged, the tunnels are tombs, and millions of people are stranded in a city that has become a labyrinth of flooded basements, collapsed buildings, and streets piled with the wreckage of everything that floated. This is not speculation. This is extrapolation from the damage patterns of Sandy and Ida combined with the hydraulic modeling that the Army Corps of Engineers has performed for exactly this scenario. The models exist, the numbers exist, the maps exist. They show that a storm with a 20-foot surge at the battery, combined with 12 inches of rain over 24 hours, would inundate more than 50 square miles of the metropolitan area. That is an area larger than the entire city of Paris. The water would reach as far north as 34th Street in Manhattan, as far east as the Van Wyck Expressway in Queens, as far south as the outer reaches of Staten Island, as far west as the Meadowlands in New Jersey. More than 2 million people live in that inundation zone. Not visit, not work, live, sleep, raise children, grow old. 2 million people who have never seen the map, who do not know that their home is built on land that was underwater 2 centuries ago and will be underwater again. And when the water comes, it will not ask for identification. It will not check flood zone designations. It will simply fill the space that gravity has assigned to it. Now let us expand the scale again. Because the perfect storm is not just a New York problem. It is a template. Every coastal city on the Atlantic seaboard has its own ghost storm, its own historical surge, its own neglected vulnerability. Boston has the hurricane of 1635, which pushed a surge that Native American oral traditions described as the ocean rising over the islands. Miami has the Labor Day hurricane of 1935, which killed hundreds of World War I veterans working on a railway in the Florida Keys. New Orleans has Katrina, which is not a ghost but a living memory, a wound that has not healed. And each of these cities is engaged in the same psychological struggle as New York. The struggle between the knowledge of what is possible and the cost of preparing for it. The struggle between the short-term horizon of politics and the long-term horizon of climate. The struggle between the individual's right to live where they choose and the community's need to avoid paying for that choice when disaster strikes. These are not engineering problems. They are not even political problems. They are philosophical problems. They are questions about the nature of risk, the distribution of responsibility, and the value of a human life that is statistically likely to be lost in a future that feels unreal until it is present. But there is a deeper layer still. Because the perfect storm is not only a convergence of water and wind, it is a convergence of timescales. The geological timescale of the sea level rise that has been accelerating since the end of the last ice age. The astronomical timescale of the tides that have been rising and falling for billions of years. The historical timescale of the storm of 1821, which is 200 years in the past, but only a heartbeat in the life of the planet. The political timescale of election cycles, which measure time in years. The human timescale of a single lifetime, which measures time in decades. And the experiential timescale of a disaster, which measures time in minutes. These timescales are normally separate. They do not interact. The geological moves so slowly that we cannot perceive it. The experiential moves so quickly that we cannot plan for it. But the perfect storm is the moment when all of these timescales collapse into one another. The sea level rise that has been accumulating for a century becomes, in the span of an hour, a wall of water at your door. The tide that has been predicted for millennia becomes, in the span of a minute, the difference between survival and drowning. The storm that was a statistical abstraction becomes, in the span of a second, the last thing you ever see. That is the true nature of the perfect storm. It is not just a weather event. It is a temporal event. It is the moment when the slow violence of climate change and the fast violence of a hurricane become the same violence. And our minds are not equipped to hold that simultaneity. We can think about sea level rise. We can think about a hurricane. We cannot think about them together, because together they violate our intuitive understanding of cause and effect. The cause of sea level rise is decades of emissions. The effect of a hurricane is days of destruction. Connecting them requires a cognitive leap that most people never make, and that failure to connect is the hidden variable in every disaster model. The models assume rational actors who respond to information, but the information is meaningless if the connection is not felt. Let us go back to the basement apartments, because this is where the connection becomes visceral. The people who drown in basement apartments are not statistics. They are specific people with specific names and specific stories. In Ida, 13 people drowned. They included a 2-year-old boy and his parents, a 70-year-old grandmother, a college student who had just moved to the city. They died because the water rose faster than they could climb, because the doors to their apartments opened inward, and the pressure of even a few feet of water against a door is far more than a person can push against. So the escape route seals itself. They died because the windows were too small to climb through, because the electrical system shorted and the lights went out and they could not see the stairs, because the stairs themselves became waterfalls. They died because nobody knew they were there, because basement apartments are often illegal, unregistered, invisible to the city's emergency response systems. They died because they were poor. That is the uncomfortable truth that disaster modeling tries to avoid but cannot. Poverty is the most powerful amplifier of risk. It determines where you live. It determines whether you can afford flood insurance. It determines whether you can evacuate. It determines whether you have a car, a credit card, a friend with a couch in a safe neighborhood. The perfect storm does not discriminate. But the consequences of the perfect storm discriminate ruthlessly. The wealthy will be in high-rise buildings with backup generators and private security. The middle class will be in the suburbs, connected by roads that may or may not be passable. The poor will be in the basements. And the water will find them. Not because the water is evil, because the water is physics. And physics does not care about your income, but your income determines your exposure to physics. That is the cruelest irony of the Anthropocene. We have spent centuries using technology to shield ourselves from the forces of nature, and in the process, we have concentrated the most vulnerable people in the most vulnerable places. The shield is not evenly distributed, and the forces are not evenly distributed. The convergence of those two inequalities is the perfect storm within the perfect storm. Now consider the aftermath. Because a storm does not end when the water recedes, it ends when the last body is recovered, the last building is demolished, the last displaced person finds a new home. That process takes years. For Katrina, it took more than a decade. For Sandy, recovery in some neighborhoods is still ongoing more than 10 years later. For the perfect storm, the recovery would be measured in generations. The subways alone would take years to pump out, clean, repair, and recommission. The electrical system would require replacing thousands of transformers, millions of miles of cable, hundreds of substations. The housing stock would be devastated. Tens of thousands of units would be condemned. Tens of thousands of families would be displaced. And many would never return, because the perfect storm would change the calculus of living in New York. The city that never sleeps would become the city that cannot afford to rebuild. The insurance industry would flee. The bond rating would drop. The tax base would collapse. The services that remain, police, fire, sanitation, schools, would be stretched across a city that is half empty and half ruined. The economic consequences would ripple outward, because New York is not just a city. It is the financial capital of the world. The New York Stock Exchange would be underwater. The banks would be dark. The data centers would be silent. The global financial system, which depends on milliseconds of connectivity between New York and London and Tokyo, would stutter and seize. The perfect storm would not be a regional disaster. It would be a global event. Because in the 21st century, every city is connected to every other city by wires and cables and financial instruments. Drown one node of the network, and the whole network feels the shock. The storm of 1821 affected a few thousand people in a small port town. The perfect storm of the future would affect billions. That is the difference that time has made. Not the storm, the world around the storm. Let us pause and ask a question that the engineers do not like to ask. Is it possible to defend New York against the perfect storm? The honest answer is no. Not completely. Not permanently. The laws of physics impose limits on what can be built. The seawalls that would protect against a 20-foot surge would have to be 30 feet high to account for wave run-up. They would have to stretch for miles. They would have to be anchored in bedrock that is hundreds of feet below the harbor floor. They would cost hundreds of billions of dollars. And they would only protect the parts of the city that are behind the wall. The parts in front of the wall would be sacrificed. That is the logic of perimeter defense. You choose what to save and what to abandon. The Dutch have done this for centuries. They have built walls and gates and barriers that are among the largest moving structures on Earth. They have reclaimed land from the sea and held it against the tides. But the Netherlands is a small, wealthy, homogeneous country with a collective memory of drowning. The Netherlands has a culture of water management that is embedded in its national identity. New York does not. New York has a culture of finance and real estate and relentless forward motion. The past is a liability. The future is an opportunity. The present is a transaction. That culture is not compatible with the long-term planning required to build defenses against a storm that may not come for 50 years. The developers want to build now. The politicians want to cut ribbons now. The voters want to see results now. The storm is patient. The storm does not vote. The storm does not care about the next election cycle. The storm will wait, and when it comes, it will remind the city that time is not a resource to be spent. Time is a dimension. And every dimension has a boundary. We are approaching the edge of what the science can tell us. The models are clear about the physics. The hydrology is unambiguous. The history is documented. The vulnerabilities are mapped. And yet there is a zone of uncertainty that no model can penetrate. It is the zone of human behavior. Will we evacuate when we are told to? History says no. In every hurricane, a fraction of the population refuses to leave. Some cannot. Some will not. Some stay to protect their homes, their pets, their possessions. Some stay because they have stayed before and survived. Some stay because they do not believe the forecast. Some stay because they have nowhere else to go. All of these reasons are understandable. None of them will save you. The perfect storm will not be like the storms you have survived. It will be different. It will be worse. And the only way to survive it is to be somewhere else. But somewhere else is a privilege. Somewhere else requires transportation, accommodation, time off work, childcare, pet care, and the flexibility to leave at a moment's notice. Millions of New Yorkers do not have those things. They will stay, and they will drown, not because they are stupid, because they are trapped. And the trap is not made of water. It is made of poverty, of bureaucracy, of a society that has decided that the cost of resilience is too high and the cost of disaster is someone else's problem. That decision is not written into any law. It is written into the budget. And the budget is a moral document. It says what we value. And what we value, according to the budget, is not the lives of people who live in basements. That is a hard thing to say. It is harder to avoid saying. Because the numbers do not lie. We have spent billions on stadiums and airports and luxury towers. We have spent millions on flood protection. The ratio is the ratio. The storm will read the ratio. And the storm will not be impressed by our excuses. Let us go deeper. Let us go to the edge of what can be known. The perfect storm of 1821 was not the last time the alignment occurred. There have been near misses. In 1938, the Long Island Express hurricane hit at low tide. If it had hit at high tide, the surge would have flooded Manhattan. In 1944, the Great Atlantic Hurricane passed just offshore. In 1960, Hurricane Donna brushed the city. In 1985, Hurricane Gloria. In 1999, Hurricane Floyd. Each of these storms was a reminder that the alignment is possible. Each was a warning that went unheeded. And each was followed by a period of amnesia. The city forgot. The people who experienced the storm moved away or died. The newcomers did not know. The infrastructure was rebuilt to the same standards, on the same floodplains, with the same vulnerabilities, because amnesia is not a bug in human cognition. It is a feature. We forget, because we have to forget. We cannot live in a state of constant vigilance. The amygdala would burn out. The cortisol would kill us. So we forget. We tell ourselves that the storm was a once-in-a-lifetime event. We tell ourselves that it will not happen again. We tell ourselves that we have learned our lesson and taken precautions. And then we go back to our lives. That is not irrational. That is survival. The tragedy is that the forgetting is adaptive on an individual level and maladaptive on a collective level. The individual who forgets the trauma of the storm can sleep at night. The society that forgets the lessons of the storm builds on the floodplain again. The individual survives. The society repeats the pattern. And the repetition is the disaster. Now we must confront the most difficult implication of all. The perfect storm is not the end of the story. It is the beginning, because after the perfect storm, there will be another perfect storm. The climate is not stable. The sea level is not stable. The atmosphere is not stable. The return periods are shortening. The events that were once unimaginable are becoming possible. The events that were once possible are becoming probable. The events that were once probable are becoming certain. And the certain events are not the ones that keep us awake at night. They are the ones we have already accepted. We have accepted that the subways will flood again. We have accepted that the basements will drown again. We have accepted that the perfect storm will come. What we have not accepted is that the perfect storm is not the worst-case scenario. The worst-case scenario is the storm that follows the perfect storm. The storm that hits when the defenses are still broken, when the pumps are still unrepaired, when the memory is still fresh but the will to rebuild is exhausted. That storm does not need to be strong. It only needs to be on time. And it will be on time, because the climate is accelerating. The intervals between storms are shrinking. The window for recovery is closing, and we are not using the window to build resilience. We are using the window to return to normal. But normal is gone. Normal was a statistical artifact of a climate that no longer exists. The new normal is a series of disasters separated by intervals of frantic rebuilding. And each disaster will be worse than the last, because each disaster will inherit the vulnerabilities of the previous one. This is the feedback loop that the models cannot capture. Not because the models are wrong, because the models assume that the system returns to its initial state after each event. But the system does not return. The system degrades. The city becomes more vulnerable with each flood, each power outage, each displaced population. The perfect storm is not a test. It is a ratchet. It turns one way, it tightens, and it never loosens. Let us go back to the ghost. The storm of 1821. The water that rose to Canal Street. The ships that floated through the streets. The people who watched from second-floor windows as the ocean reclaimed the land that had been stolen from it. Those people did not have models or forecasts or emergency management agencies. They had eyes. They saw the water rise. They saw the water fall. They told their children, and their children told their children, and eventually the story faded into legend, and the legend faded into silence. We are the grandchildren of those grandchildren. We have inherited the silence. And we have inherited the vulnerability. But we have also inherited something else. We have inherited the knowledge that the storm happened. We have the newspapers. We have the logs. We have the data. We have the ability to simulate the storm on supercomputers, to watch the water rise on a screen, to calculate the pressure at the tunnel doors, to model the evacuation patterns, to predict the drowning. We have all of that. And we have chosen not to use it. Not because we are evil. Because we are human. And being human means living in the present, planning for the future, and forgetting the past. The perfect storm is the moment when those three temporal modes collapse into one. The past becomes present, becomes future. The water that rose in 1821 rises again. The water that rose in Sandy rises again. The water that rose in Ida rises again. And they rise together. And the city that never sleeps finally sleeps. Underwater. Silent. Dark. The lights that never go out go out. The subways that never stop stop. The city that was built on the edge of the continent, at the mouth of the river, on the floodplain of the ocean, returns to the element that created it. Not because the storm was angry, because the storm was inevitable, because the city was built on a foundation of forgetting. And forgetting is not a strategy, it is a delay. And the delay is over. The storm is coming. The water is rising. The tide is turning. And we are standing on the shore, watching the horizon, waiting for the ghost to return. The ghost remembers. The ghost has been waiting. The ghost is patient. And the ghost is already here. It has always been here. It was here in 1821. It was here in 2012. It was here in 2021. It is here now. In the rain that falls on Canal Street. In the tide that rises at the Battery. In the wind that blows across the Atlantic. The ghost is the memory of the water. And the water does not forget. The water remembers every storm that has ever been, and the water is writing the next one now. In the warmth of the Gulf Stream. In the salt of the harbor. In the basement of every building that was built on land that was once underwater. The water is writing. The water is waiting. And when the writing is finished, the water will read it aloud. In a voice made of wind and tide and rain. And the city will listen. For the first time. For the last time. For all the time that is left.